Matt. Matt! Matt!
Oh, hey.
Okay, yo, last time we were here, we did dynamics, but like, what are we doing now?
Sound.
Okay, yeah, I'm down. I can work with that.
Okay.
Let's do it.
Okay.
Tom, what about you?
Yeah, you guys have to stop lying on the couch. Though.
Okay.
Oh. Ow!
Yo! That made sound.
Let's talk about it.
Let's do it.
Okay. So sound is vibrations that travel through the air, and they can be heard when they reach our ears.
These vibrations are caused by objects that move quickly in a cycle. Yo, so sound travels in waves, right?
Yeah.
It travels in longitudinal waves, which means that the particle movement goes away from the thing making the sound.
Okay, and when these particles are closer together, that's called compression, and that looks something like this.
Oh my god.
But if it's rarefaction, they're farther apart. So something like that. Matt, take it away.
Thank you. Alright, so this red line right here is the equilibrium point. The farthest away that a wave can get from the equilibrium point is called the amplitude. And the highest point of the wave is called the crest, and the lowest point is called the trough. Alright, I'm going to pass this to Dante now.
What a catch. Wow.
Alright, so the wavelength is the distance between two similar points on a wave. So, for example, this right there would be the wavelength. And then the phase shift is the horizontal movement of the wave. So, if I were to bring the equilibrium point over here and the wave shifts across, that would be a phase shift. Okay, so anything that moves back and forth at a regular speed at a regular time interval can be referred to as simple harmonic motion. It sounds easy, but it can get kind of trippy sometimes. Simple harmonic motion.
The frequency is how many cycles a wave does in a certain amount of time. This is measured in hertz.
Okay, and the period is how long it takes for a wave to do one complete cycle.
Oh, okay. Well, the wave speed's how fast the wave goes through a medium.
So frequency is determined by taking the number of cycles and dividing it by the change in time. The period is somewhat different, and it's the inverse of the frequency. So all waves have speed. This can be determined using this equation. Speed is determined by the frequency of the wave multiplied by the wavelength, which is lambda. So the audible sound waves are what we can hear. This ranges from 20 hertz to 20 kilohertz.
Infrasonic sound waves are sound waves we can't hear, and they're below the audible range.
We also can't hear ultrasonic waves, and these are above the audible range, or above 20 kilohertz. So if I have a dog whistle and I blow on it, we can't hear it, but Chase can.
He's like Spider-Man.
It might only sound like air to us, but he can definitely hear that.
So the Mach number shows how the speed of an object compares to the speed of sound. If the Mach is less than 1, it would be subsonic. If the Mach is greater than 1, it would be supersonic. And if the Mach is greater than 5, it would be hypersonic.
Alright, so the speed of sound is all dependent on what the temperature is. This is the equation right here. The speed of sound, or the velocity of sound, is equal to 331.4 meters per second plus 0.606 meters per second Celsius multiplied by what the temperature is. So if it was 13 degrees Celsius, it would be Vs is equal to 331.4 meters per second plus 0.606 meters per second Celsius multiplied by 13 degrees.
Okay, so we're going to talk about Medalla boundaries. Oh! Okay, as you can see here, the big snake eats the little snake.
No!
Oh, God!
Okay, in medium boundaries, we have the thicker medium and the thinner medium, the more dense medium and the less dense medium, right? In a free end system, the more dense medium would transmit the wave to the less dense medium, but it would transmit the wave to a smaller wave. In this case, in the fixed end, the thicker medium would transmit the wave into an inverse wave, but still smaller.
Oh, hey, didn't see you there. This right here is a standing wave. It happens when two identical waves collide. This on the end is the node, and in the middle here is the antinode.
This can also be seen in string instruments. So if I pluck this string, that's a standing wave.
So the fundamental frequency is the lowest frequency that can produce a standing wave. Harmonics are whole number multiples of the fundamental frequency.
Reflections. These occur in large rooms, like the one that we're all in right now. Here, you can encounter reverberations. These are when you hear sounds, and in a fraction of a second later, that same sound is heard. These are also called echoes. Hey, Tom!
Oh, hey! Oh, hey! Oh, hey! Oh, hey! Oh, oh. Hey, I didn't see you there. Oh.
That's a weirdo. Anyways, in this room, we have pretty bad acoustics. This is why we can hear echoes. So if I scream the word, hello, there's an echo. Let's go inside. Right now, it's winter, and everything's kind of covered in snow right now. So right now, if I scream the word, hello, it's not too much of an echo. These are good acoustics.
Yo, that was the Doppler effect.
That's an example of the Doppler effect, because when Matt was coming closer to us, the sound waves were traveling more condensed, because he was coming at us with more sound waves traveling. As he passed, the sound waves started to come to us a little bit slower because he was traveling farther away. Okay, so the equation for the Doppler effect is the frequency of the observer is equal to the speed of sound plus the speed of the detector divided by the speed of sound plus the speed of source, the speed of the source, and then you multiply that by the frequency observed.
Alright, there's two types of beats. There's acoustical and rhythmic. This is a rhythmic, it's what you hear in music. And in physics, there's acoustical beats. And these are a change in the sound's loudness over time. Next we got damping. And damping is just the reduction in the amplitude of a wave.
Resonance. The resonant frequency is the frequency at which a medium can vibrate the easiest. Resonance is when the wave equals the resonant frequency. That's right.
Overtones. These are the sounds that are usually produced by instruments, and I say usually because other things can produce them too. So, for example, if I were to pluck this violin string, or if I were to beautifully play this violin string, those are overtones that are being produced. Sit back down. Those are overtones. See, Tom?
I don't think so.
Oh. Well, there he is. Anyways, it's musical
Oh, hey!
instruments. Musical instruments.
Didn't see you there.
Anyways, musical instruments. These are musical notes, and that's noise. This is what musical instruments produce, and that is what they don't produce, unless played horribly. So, there are three categories of musical instruments: string, percussion, and wind, and we'll each talk about our own instruments.
So, string instruments are played by plucking a string that's fixed at both ends. This would usually produce a first harmonic, but other harmonics can be produced depending on where you pluck the string.
Alright, percussion is just the striking of one object against another, like this. There's three types: single indefinite pitch, multiple indefinite pitch, and variable pitch.
So, next is wind instruments. I have a whistle as my example. So, wind instruments are usually made by resonant air columns that are usually open on one end, and the sound can usually depend on the length of it.
Alright, so these are sonic booms. When you have a plane or any other object that's stationary, the sound waves around it are spreading out evenly. But as you can see with our plane here, once it starts to move and catch speed, the sound waves start to spread out behind it, but they're bunching up in the front here. And as this plane reaches very high speed, the sound waves bunch up so much, and it breaks what's called this thing, the sound barrier, And so that creates a large shock wave, which hits the ground, and we hear it as a large boom. Boom!
That concludes our sound ELI5.
Thank you for watching, and also special thanks to our cameraman James. And yeah.
Have a Merry Christmas.
Yeah.
I am Russian spy Professor Zoidberg.
Ready?
I feel like we should do something else. I feel like we should do like. Hey, Matt. Didn't see you there. Matt.
Oh, hey, didn't see you there.
Matt.
Oh, didn't see you there.
Yo. I made sound.
Bro, I made sound.
Oh my.
In a cyclical what? Yo, so sound travels in waves, right?
Thing.
Oh my god. And that's when the particle movement goes the same way coming from the sound. Wait.
So this little red line right here, that's the Alright, it's the equilibrium point. Okay, so that's it for me. Pass it to Dante here. Oh my gosh.
It is how long it takes for a wave to do one cycle.
What?
Wavelengths are with the. Oops.
Hi.
No.
Oh hey. Oh hey. Oh hey. Oh hey. Didn't see you there.
This occurs.
This occurs. Oh. Hey. Didn't see you there.
Action.
Harmonics are whole number multiples. Harmonics are
Yo, that was the Doppler effect!
No! Come back over here! Basically, the frequency of the observer is equal to the speed of the.
But in physics, they're called acoustical beats. Next is damping. So damping, I have no clue what damping. Oh wait. So that's a rhythmic beat. A rhythmic.
So string instruments are no. Do we have to talk about the instruments
Yes.
first?
Oh. And that's noise. This is what music gets. Where's Tom? Oh.
You're supposed to start.
I thought you were gonna say something.
No, you start and I interrupt you.